Okay, so we'll get started here. Just some basic stuff. Basically, somebody has made a histogram for us, done the work of calculating these probabilities that we calculate in this section. And by saying the probability of x equals 2, let's imagine what this histogram could represent. Maybe we ask 4 people a question, a survey question. And we want to know what's the probability that 2 of them say yes. That's what this is saying. X represents the number of people who say yes to this question, and x equaling 2 means 2 people said yes to this question. So what's the probability that x equals 2? What's the probability that 2 people say yes to this survey question? Well, looking at the histogram, we don't have to use that formula. We don't have to do anything tricky. The probability clearly is 0.3. Okay, what's the probability that the number of people who answer yes to the question is even? And that would just be the probability that x is equal to 2 plus the probability that x is equal to 4. These are non-overlapping events. We just add them together. You can't have 2 people answer exactly 2 people answer yes and exactly 4 people answer yes. Okay, and that's what this is calculating. It's not 2 or more. It's not 3 or more. It's exactly 1, exactly 2, exactly 3, exactly 4. So what's the probability that exactly 2 of the 4 people will answer yes? We already have that, 0.3. Plus, what's the probability that exactly 4 people will answer yes? That's 0.2. And that comes out to be 0.5. Next, we actually have to do some work here. I had started this before, forgot to erase that. Okay, so let's rewrite that down, and then we'll talk about why we do it that way. All right. Well, we're going to have 15. These are called trials. This is the jargon for it. We want to have 6 successes. All right. So we always are going to use this formula this way. We're going to have a combination. So we're going to have trials, successes. So it's going to be 15 choose 6, 15 C6. Okay, what's next? Well, now we have the probability of a success. Let's call it capital S a success. Okay. But not just that. Let's start with it though. What's the probability of a success? Well, the probability of what's a success? Getting a heads. What's the probability of getting a heads when you flip a coin? It's 0.5. All right. And then we raise that to the number of successes we want to get, which is 6. We want to get that many successes. So successes goes there, and it goes right here. All right. Next, we're going to multiply by the probability of f. Let's call f failure. Okay. And by the way, this is what we call lowercase p, and this is what we call lowercase q. So what's the probability we won't succeed? What's the probability we won't get a heads? So that'd be getting a tails. That would be also 0.5. And we're going to raise that to the number of failures. Well, if we succeed 6 of 15 times, then we must fail 9 times. All right. So there you go. That's it. That will give us the answer, 15C6 times 0.5 to the 6 times 0.5 to the 9th. That will be the answer. But let's see why. Okay. Well, first let's consider getting 6 heads out of 15. How could that happen? Well, we could get heads, then a third heads, then 4, then 5 heads, and then a 6th. Then the rest would be tails. Okay, you might recall from class, or if you watched the lecture video, this is not the only way this can happen, but let's talk about how likely this is. Well, we'll get our first heads a half of the time. Then we'll get a second heads a half of that half, and then a third heads a half of a half of a half. This is all from 10.5. You know, that things happen all in sequence like that. We just multiply the probabilities together. Well, we keep having a half and a half and a half. So the probability that I'll get 6 heads in a row is a half to the 6th. Oh, look at that. A half times itself 6 times. That's where that comes from. Then the probability that I'll get the following 9 to be tails is also, each tails has a probability of 0.5, 0.5, 0.5, 0.5, 0.5, all the way down. So we multiply all of these together. Well, this part would be 0.5 to the 6th. This would be 0.5 to the 9th. Okay? And that's where 0.5 to the 6th and 0.5 to the 9th come from, because we're going to have 6 successes and 9 failures. So the probability of a success is going to be multiplied by itself 6 times, number of successes. And then the probability of failing will get multiplied by itself the rest of the times, 9 times. Okay, but if you multiply that together, it will not come out to be this, it'll just come out to be this part of it. Right? What's this about? What this is about is this is not the only way that we can get 6 heads. We could get 5 heads, a tails, and a heads again, and then the rest tails. Right? Well, this still has a probability of 0.5 times itself 6 times, 0.5 times itself 9 times, so it still has the same probability. The specific arrangement has the same probability as this one up here does. We would just add them together, right? It can happen this way, or it can happen this way, or it can happen this way. Heads, 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 tails, tails, heads, and then the rest tails. So you can see, you start to see how there are many, many ways to get 6 heads. We can move this H all the way down the line, then we can move this second last H all the way down the line, and then it would get kind of hard to count, but we can use combinations to count this, okay? Because what are we doing? We only have 2 things that can happen, either heads or tails, success or failure. So if I listed all of these possibilities out, I would just add them all together, right? So the question is, try and shrink all this down. You know, if I could list all these out, and that would be a lot. I would list out heads, 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 and get another way that could happen, and another, and another, and another. All these different ways that I can get 6 heads out of 15. Well, I would take all of these, which have the same probability, that's what you want to keep in mind. All of these are 0.5 times itself 6 times, and times itself 9 times, and multiply that together. This is 0.5 times itself 6 times, 0.5 times itself 9 times, multiply those 2 together. So all of these have the same probability, every one of these. So if we knew how many there were, we could just take that probability and multiply by the number of ways that you can get 6 heads out of 15. Well, what we're really doing is choosing, out of these 15 positions, 6 places, 6 unique places for the heads to go. Okay? And in short, that is 15C6. There are 15 places, 15, let's imagine them as chairs, for these heads to sit. Okay? And I want to find out how many unique ways are there for these heads to sit down in all these different chairs, right? They could sit down on the first 6, or the first 5 and the 7th one, or the first 5 and the 8th one, or the first 5 and the 9th one, and so on and so on and so on. So I'm just really picking numbers from 1 to 15 in groups of 6. How many ways can I do that? 15C6. Okay. So all the ways that we can get 6 heads, that's 15C6. So since each of these has the same probability, and we can now count how many ways that probability can come up, we would just take 15C6 and multiply it by the probability of every possibility, you know, having the same probability. Everything has the same. It's 0.5 to the 6 times 0.5 to the 9th. Rearranging where the heads are doesn't change that. That probability is still the same. So, with all that long explanation out of the way, let's calculate this. 15. Get our combinations. That's 6. Let's just hit enter. Times 0.5 to the 6th times 0.5 to the 9th. So altogether we have a little over a 15% chance that this will happen. 0.1527. And this was, I think it said 5,005 ways this could happen. Yeah, 5,005 ways that can happen. So 5,005 ways to have something happen that has a probability of pretty small, 0.00003. We just multiply that by 5,005 different ways that it can happen, and we get our probability of 0.1527. Okay. So let's say we have a 35 question quiz. It's a, let's see, 35 question multiple choice. Let's say each multiple choice has 4 choices each. So it's a multiple choice quiz, test, whatever, and you didn't study very well, and you're just gonna completely guess every single question, or maybe for some reason you're, in China, you don't speak Chinese and you don't know how to read the questions, but you can guess on every single question. All right, so we want to know what's the probability of, when C represents a number guessed correctly, what's the probability you'll get 17, exactly 17 correct? So really quickly, let's just go to the answer. All right, so we're going to have 35 questions guessed. We want to see how many ways that we can guess 17 of 35. I can guess the first 17 correctly, and the last not correctly. I'm going to guess the first 16 correctly, miss the 17th, get the 18th correctly, and the rest will be incorrect. Right? We're counting all the ways that can happen. Then we're multiplying it by the probability of of each of those scenarios. Okay. So if I had the first 17 correct, what would be the probability that I get 17 in a row correct? Well, the probability that I get any question correct would be 0.25, since there's 4 choices for each multiple choice question. Okay, I'm going to take 0.25 times 0.25 times 0.25 17 times. Okay, but the rest of the time I'd have to fail. So I multiply 0.25 by itself 17 times, then I'd multiply by 0.75 the rest of the time. So 35 minus 17. I'm going to make sure I get this correct. The simple arithmetic makes me the most nervous. 18. Okay, couldn't get much better, easier than that. So this is the probability that that I'll get specifically 17 correct in a particular 17 questions correct. The first 17 correct, and the last 18 not correct, or the first 16 correct, the 18th correct, and all the rest incorrect. Every single every single specific arrangement of 17 correct questions will have this probability. And 35C17 is the number of ways that I can, of which questions I can specifically get correct. So we throw all this together. 35C17 times 0.25 to the 17th times 0.75 to the 18th. Make sure all that's going to come out correct. That looks good. So 0.0015. 0.0015. Not a very likely scenario. Okay. Next we'll look at what's the probability that we get exactly 20 correct. All right. So we are guessing at every one of these 35 questions, and we want to see what's the probability of getting 20 of them correct. So again, we're going to take the 35 total questions, and 20 of these are going to be correct. 20 of these are going to be successes. Right? They're going to multiply by the probability of a success. That's not very surprising, right? 0.25 to the 20th, because if we get 20 questions correct, we're going to get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20 of them correct. And then we're going to get all right, so that should be a total of 35 little dashes, and 20 of those are going to be correct, and 15 of those are going to be incorrect. The probability that you'll get 20 correct is just 0.25 times 0.25 times 0.25 times 0.25 20 times. The rest of the probability that you would continue to multiply together would be the probability that you don't get that question right, that particular question right. So then we're going to multiply 15 of those together. And that's the probability, like this is the specific probability, just this part is a specific probability that I'm going to get, say, the first 20 correct, and then the rest not correct. But then there's, I could get the last 20 correct, I could get the middle 20 correct, I could get the, and they don't even have to be in a row. I could get every other one correct, maybe until I get 20 correct. So we're going to have to count all those, and that's what this part is doing. It's counting all the possibilities. This counts the one way that we get all the first 20 correct, the last 20, the middle 20, every other one correct, all that kind of stuff, and essentially adds this probability to itself that many times. So, in the end, the probability of getting, and the mistake that a lot of people make is thinking that this probability is going to be the probability that you get 20 or more. That's not the case. It's exactly 20. So, 35 C 20 times 0.25 to the 20th times 0.75 to the 15th. And so this is really unlikely, which shouldn't surprise you if you have a very poor chance of getting any one question correct, and you're trying to get 20 out of 35. Maybe 20 out of 1,000 is a pretty good probability, but 20 out of 35, that's pretty high. And to get exactly that many is really bad probability, so 0.0000039. Okay, now we want to calculate the probability similar to what I referenced a couple seconds ago, of getting less than or equal to 4 successes out of 12. Okay, so we need to calculate the probability of getting 4 successes or less than 4 successes. So the probability of 3 and of 2 and of 1, and also don't forget 0, because that's definitely less than 4. Okay, but each of these are calculated exactly the same way that we've been doing so far. So 12C4 times the probability of succeeding is 0.43. I'm going to raise that to the 4th times 0.57 to the rest of the time. That would be 8. Alright, then we're going to add on this probability, right? Because this could happen, or this could happen, so we're going to add them together. 12C3 times 0.43 to the 4th times 0.57 to the 8th. No, excuse me. 4 and 8 are no longer correct. We're going to have 3 successes, and we're going to have 9 failures. And 12C3, 0.43 to the 2nd, sorry, C2. We're going to have 2 successes here, times 0.57 to the 10th. 12C1 times 0.43 to the 1st times 0.57 to the 11th, and finally all of them are failures, which would really just be 0.57 to the 12th. Right? There's only one way that all of them can be failures. You fail every single time, and that would be 0.57 times itself 12 times. So that's how we would handle that. I'm going to leave it to you to multiply this out, but to be very specific, we're going to multiply these together, and we get that probability. And we get this one, and this one, and this one, and this one. And these are all like separate. You can't get exactly 4 and exactly 3, so this is what we call not overlapping, right? Disjoint. So we would take this, and we would add this, and we would add this, and add this, and add this. We'd add all the probabilities together. Okay, so here we used previous data to make predictions about the future. This happens a lot. So David Beckham completes 47 of 66 passes. So based on this data in this game, he makes 47 of 66. He makes about 0.71 or 71% of his passes successfully. So in the future, you would expect him to have about a 71% chance of completing a pass. This is not a good sample size. It should be more. We should look at maybe his last 100 or 500 passes and see how well he did there. But this is what we have. So that's why it says if he keeps this up, if he does, what's the probability that he will complete 50 of his next 75 passes? Okay. Well, this is exactly the same situation. We have 75 trials of the experiment him being, he passes the soccer ball. And we want to have 50 successes. P, right, the probability that he succeeds, we're going to take to be 0.71, because that's what he's shown himself to be able to do in the recent past. So we have 75 trials. We want 50 successes. This is how many ways that he can have 50 out of 75 successes, right? The first 50, the last 50, the middle 50, and every other combination possible. The probability of a success is 0.71. He's going to have 50 successes, so we're going to raise that to the 50th power. He's also going to have a certain number of failures. He's going to have 25 failures in this assumption. And the probability that that would happen is 0.29. So we multiply this all together, and that's going to be the probability that he gets 50 out of the next 75 passes. I'll run that real quick. 75 C50. That's 75 C50 times 0.71 to the 50th times 0.29 to the 25th. So the probability that he gets exactly 50 of his next 75 passes based on the success rate he's had recently is 0.07, we'll call it, 0.07. So like 7% chance that he'll complete 50 of the next 75. Now if we wanted to calculate at least 50 or as many as 50, we would have to then calculate, like at least 50, we'd have to calculate 50, 51, 52, 53, all the way up to 75, add all those probabilities together. Then we would have a picture of how likely it is that he'll score or complete at least 50. Or if we wanted to do at most 50, 50 or fewer, then we would have to do 50, 49, 48, 47, exactly like we did here, but with replacing 50 and 25 with the appropriate numbers. All the way down to 0, 3, 2, 1, 0, and then add all those probabilities together. Or we could take the probability that he'll get, since it's going to be less work, 51, 52, 53, 54, all the way up to 75, and then subtract that from 100%, and that would give us the probability that he scores at most 50. Or I guess that would be at most 49, because if we include 50, then we're cutting the line at 49.50. Thanks for watching.